Hello, everybody. Welcome back to the ICCI Pavilion. I'm Jonathan Willey, an early career scientist volunteer, and it is my pleasure to bring us onto our next session. We're discussing predicting the future of ice in a warming world. We have a series of experts on various topics of mountain glaciers to join us today. Well, in order, we have Dan Morgan, Regina Hoke, and Fabian Massino. So let's begin with Dan. Podium is yours.
All right, thank you, everyone. It's nice to see you all, and I'm looking forward to sharing a little bit of a paleo perspective on helping predict future warming here. So just to get us going here, I always start off by thanking all my collaborators. A lot of students have worked with me on these projects over the years, and of course, funding agencies, National Science Foundation, United States Antarctic Program, Vanderbilt University has funded a lot of these things. The Scientific Committee on Antarctic Research has funded some of this. So lots of people have worked on these projects, and I'm going to share a lot of work from other folks too, who are not direct collaborators, but are people that are doing a lot of work in this field. And then just to briefly introduce myself, so I'm Dan Morgan. I'm from the United States. I grew up on the west coast of the United States, and then I moved to Tennessee for a job in 2009, where I work at Vanderbilt University. I'm there in the Department of Earth and Environmental Sciences, and I'm also one of the associate deans in the College of Arts and Science, in part because I really like to help provide experiential learning programs for students. So I do a lot of research with students, try and help them find research opportunities, study abroad, internships, ways to really get themselves and their hands dirty and get out there. And I'll show a bunch of pictures of the students I take to Antarctica and all this. And then as a scientist, I'm really a geomorphologist. So I may be a little different than many of the people that have spoken here in the Cryosphere Pavilion, because I'm really looking at the dirt and the landforms and the landscapes that glaciers leave behind. I'm not really on the ice all that much. And so I'm really interested, though, in the stories that landscapes tell, how we can interpret them as representing past environments and how those environments have changed over time. And I get to do a lot of work in lots of mountain areas, including Antarctica, but in the Rocky Mountains, Sierra Nevada, down in the Andes. I've been out to Iceland and the Himalaya, and yeah, lots of places. Anywhere there's mountains, I like to be there. Okay, so just a brief outline. I'm going to walk through a little bit of my interest and motivation in all of this. I'm going to talk really briefly about the primary methods that I'm going to discuss today and that I use in a lot of my research. And then I'm just going to go through some examples of recent research projects in Italy, out in Colorado, and then a bunch down in Antarctica, and wrap things up from there. So just to get started, as I said, I'm a geomorphologist. And so I love pictures like this that are just sort of what's going on the Earth's surface and what kind of stories do they tell. You know, in architecture, there's this phrase that form follows function. You know, you're going to design something to meet the needs of that space. In geomorphology, we kind of twist that to be, well, the form, the shape of something follows the process that created that landscape. We're really trying to understand the physical processes that are active there, when they happen, how fast they happen, how they represent environments and environmental change that way. So a lot of my work is, yeah, what processes, what environments created these landscapes, when, how fast, how much. And then lots of folks have showed this slide or this kind of video, and this is the GRACE satellite showing mass loss from Antarctica. It's obvious that we know we're losing lots of ice. The big question is, well, how much are we going to lose in the future? How fast will it change? How will sea level change? How will water resources, ecosystems, communities have to respond to all of this, right? That is always our big picture change. So lots of folks build predictions and models to sort of how might the Antarctic ice sheet change? And I've just picked one of them here. This is from Dave Pollard and Rob DeCano. There are a bunch of models like this, but hopefully you can see a couple of different pathway scenarios here, and Antarctica might contribute a meter or up to 15 meters of sea level water equivalent in the next couple hundred years, right? But you do have to ask, how well do we know these predictions? How well do we trust them? Well, that's where I start to come in, because one of the ways we test these models is that we start to run them backwards in time. Or can we recreate the past? So this is these same folks, Dave Pollard and Rob DeCano, an earlier paper of theirs, where they're trying to sort of model the change of Antarctica in the past. And then we can compare how well do these models capture the information we see in the landscapes in Antarctica or in offshore records. how well do they line up with what we find from the historical record and the geologic record that way? And that's where I come in. I'm really interested in figuring out what has happened in the past. So just to give you a quick little introduction into the methods I'm going to use, I know this isn't a pure science talk, but I like to talk about this because it's fun. And really what I'm talking about are cosmogenic nuclides, which are high energy protons and neutrons that Earth is always being bombarded with. They come from supernova explosions, and they have enough energy to work their way through the atmosphere. They cause a bunch of reactions with the atmosphere. This is how carbon-14 gets made in the atmosphere. But enough of them have energy that they'll actually penetrate the upper few meters of Earth's surface and can create new isotopes in the crystal lattice of minerals, which is really cool. So the simple one that I'll use a lot today is that some of these neutrons might come down and hit oxygen that's in the quartz crystal lattice. Quartz is the silicon and oxygen, and it might turn some of those oxygen atoms into an isotope of beryllium, beryllium-10, which is really rare. And this is really the only way beryllium-10 is formed in quartz minerals on Earth's surface. So it's really great because these quartz minerals start off with zero of it, and they only build up beryllium-10 when they're exposed to these cosmic rays, which are mostly in the upper few meters of Earth's surface. So the application of this for glacial geology has been great because glaciers are really good at covering landscapes, scraping up rocks from underneath them, and then depositing them at their margins. So they start off with zero of these isotopes and start building them up once they're exposed at the margins, or once the ice is finally retreated out of there. So I'm going to do a little bit of both collecting soils and boulders left at the margins, but also the bedrock that was underneath the ice to figure out when did this get exposed? When did ice leave this area? Sometimes you'll hear it referred to as a suntan clock analogy, which is only okay in part because these cosmic rays are not created by the sun. The sun's not big enough to create them. But it is kind of fun. This is a picture of me coming back from Antarctica where I haven't showered for 40 days. And you can tell I'm pretty sunburned. And if you knew how quickly I was, kind of building up pigment in my skin, you could kind of date how long had I not gone with a shower, right? And you can almost see it in some of these rocks too, where the rocks are getting redder because they're oxidizing. They're out there. Again, it's a different process, but that is how long they've been exposed. The rocks are almost getting sunburned too, right? So we collect a bunch of samples in the field. We bring them back to my lab at Vanderbilt. We go through a bunch of processes to get just the quartz minerals out of them. Then we mail those off to a lab either in Purdue or in California, and they'll be measured, those rare isotopes, on an accelerator mass spectrometer. And basically the amount we measure, we can translate into an age. How long has that stuff been exposed? So let's jump into some fun examples of this. So I've started a collaboration with Mauro Guglielmin, who's at Insubria University up in Varese in Italy. And this is fun because we get to go near Lake Como. So Como's in the southwest corner of the map area there. And you can see Lake Como up there and the big valley that is filled in there. So let's go. That's what a glacier would look like in that area 19,000 years ago. So some folks have dated kind of the end of that last glacial maximum is about 19,000 years. And that valley's about 160 kilometers long, depending on where you go and end up in. And we went kind of interesting. We wanted to know, well, when did the little high mountain pass areas become ice-free? So we went to a few of these different areas. Let's see, does that work? Oh, maybe. No, I can't see it, but Valviola, Stelvio Pass, Gavia Pass are the high mountain passes that are ice-free now. And we wanted to know, well, how quickly did ice retreat back through there? Again, we want to make predictions on how fast is ice going to melt in the future. We can look to the past to figure out how fast it went. And also there's some different theories on sort of the style of deglaciation. Did it just kind of retreat from the snout all the way back? Or did it actually retreat from the top and the bottom at the same time and leave ice in the middle for a longer time period? There's different theories on sort of the style of deglaciation. So we go out to these field areas, we collect a bunch of rocks. Here we are, we're standing here in Valviola. We're right on sort of the Swiss border, which I love is just a little string and some fence posts at that part of the world. But collected a bunch of samples just of the bedrock to figure out when did the ice retreat and expose all this. And we get answers that are around 14,000 years. And it's interesting because that highest sample actually seemed to get exposed first, about 14,300 years ago. And then samples that were lower down on the valley floor didn't get exposed until 13,000 years ago. So this is some evidence that actually says, all right, the ice says it retreated, actually retreated from both the top and the bottom here in Valviola. Of course, it wasn't as simple as that. I mean, we would go over to Stelvio Pass. We got kind of different answers. Um, One, they're actually quite a bit younger, suggesting that ice stayed in Stelvio for a much longer time. You see some of these ages are only 10,000 years old. Um, there are some younger ages of 6,000, but I'm actually not so sure that was a good sample to collect because this is an area that has had a lot of human activity. Actually, during World War I and II, there was a lot of human activity around here. And if humans pick up rocks and move them around, they're changing the surface. And then they may expose new rocks that may not have, yeah, I may not measure the correct thing. So some of these older samples, I have pretty high confidence that glaciers have really covered that area. The younger samples, we have a little less confidence that they weren't moved by people. And so I kind of stick with, all right, this was at least ice free by about 10,600 years or so. We go over to Gavia Pass and we are getting answers, somewhere around 10,800 years. What's kind of interesting is that the high pass area and all the valley floor samples we collected really all overlap with air. So this is not showing sort of a slow decline or a rate of change at all. It's really kind of indicating pretty fast deglaciation. Well, not fast, but all happening at the same time in that sense, at about 10,800 years or so. The other thing that we're interested in here are some geologic hazards. So what's fun is these methods, we can date glacial things really well, but we can date, flood deposits, landslides, anything that makes a new surface. And so this is the work really of Alessandro Longhi, was a graduate student working with Mauro, and he actually mapped out this area as his master's thesis, creating a really detailed geomorphic map, identified a bunch of landslides that were in the area, and he actually found at least two. There may be a third one as well. We collected a bunch of samples from those boulders to figure out when did they get deposited. And here what's interesting, there's sort of, again, multiple theories for what might cause these hazards. One idea is that when ice filled that valley, it sort of supported the mountain walls. And when that ice retreated and then wasn't supporting those walls, the landslides would have happened really frequently or right after the ice was gone. Or another idea is the ice is in there, it retreats. There's a lot of permafrost in the soil and perhaps buried ice from the glacier that's in the soil. When that eventually melts out, that might cause some of these landslides. And so that might have a different timing, though, than just happening right after the ice retreats. So we wanted to test some of these theories on what might be the triggers for these landslides. So we got ages that were much younger than when the valley floor was deglaciated. So remember that valley floor was about 13 or 14,000 years that it was deglaciated. These landslides are happening around 7,000, 7,700 years ago. So this is some evidence that suggests that it was probably more related to permafrost melting, which gives you some insight perhaps into what we might predict for future hazards in the area as temperatures warm, and we certainly know more permafrost is melting in this area. We might be susceptible to a lot more landslides as a result of that. All right. So just if I had to kind of summarize Italy here quickly, we can see that some of these mountain pass areas are ice-free by 13,000, 10,000 years or so. And then we can calculate sort of average retreat rates. We know the ice was down at Como at about 19,000 years, so we get retreat rates of on the order of 10 to 30 meters per year on average, right? That's a long-term average, right? So there may have been times where it was a little faster or a little slower. We want to go back and collect more samples along the valley floor to get a little more detail into how that actually played out. But this is interesting. It's also interesting that they're not all the same age, right? There are definitely some local variations of a few thousand years, and it's worth actually remembering that in Forney, where that picture of the student was, there are still glaciers there, right? So they're not actually all gone either, right? So while we went to mostly areas, all right, where they're all gone now, yeah, there's enough local variation that some places have held on to their glaciers there. And so that's actually a lot of Alessandro's PhD work is really looking at the local variations between all these valleys, which there's quite a bit. And so you need that really detailed information to make really good predictions. All right, let's jump over to Colorado, where I've really just begun starting some projects here with students. I get to take my students on a 5-day field trip to Colorado. So we were there in September. We've done that the last few years, and we're mapping out glacial deposits, dating them, and again, looking at kind of deglaciation rates in here. Again, context is if we go over to Rocky Mountain National Park, which is in Colorado, a little north of the area, there are a handful of little glaciers hanging on, although they might not be true glaciers anymore because they're not may not be flowing all that much right now. But here's the Andes Glacier. You can see in basically the last 100 years or so, it's retreated about 100 meters, and so you're getting retreat rates on the order of a meter per year or so, which is pretty noticeable over here. So if we go to the field area we're going to is a little south. There we go. Oop. And so here's one paper written by a bunch of folks from University of Buffalo, Colorado College, where they went out to the end moraines and dated a bunch of these. And this is fun because we get to see some deposits in sort of the bottom right corner there are actually from the penultimate glaciation. So the second to last one, they're about 120, 130,000 years old. And we get excited when we find those because often glaciers are coming and going in the same place and wiping out their same landforms. So you don't always get to see that. And then we see a lot of these end moraines, the last glacial maximum of around 20,000 years. There's a little retreat, and then there's another little moraine at about 15, 16,000 years that you can see there. So then a couple other colleagues went and did this kind of in a broader area, but did this kind of deglaciation project. And also, so they dated a bunch of moraines, or they used some existing data for the end moraines. They collected bedrock samples along the valley floor, as well as the high mountain pass areas. And this is interesting because now you get these deglaciation rates, right? So you can see that sort of last glacial maximum extended about 20, 22,000 years. There's a little retreat of just on the order of 5, 10 meters per year. There's a little moraine gets built around 15, 16,000 years. But then between there and about 13,000 years, there's really rapid decline of these glaciers, and the high mountain pass areas are ice-free by 13,000 years, 14,000 years ago in all of these areas. And so you're getting then retreat rates on the order of 7 to maybe up to 35 meters per year from all of them, right? So it's really interesting, and interesting that they're kind of in line with what we see in Italy and the central Italian Alps as well. All right, so then we're going to switch over to Antarctica here. And so yes, perfect. So just to do a quick introduction to Antarctica, and I'll try and do it quickly, but I really like talking about this, so I might go on a little longer. But if you had to remember one thing, I always put this slide up. Antarctica is the most continent. It's the iciest, coldest, highest, brightest. I like to say loneliest and least explored. It's the only continent with no indigenous humans in it, right? It's basically empty. When we go out there, we usually don't see anyone else except for the 4 or 5 of us in our field party for the 5 weeks that we're camping out there. And it's also the world's largest ice sheet. It's equivalent to about 60 meters or so of sea level rise, right? This is about 90% of the ice that's in the world is collected here. And again, I like to set up kind of this long-term geologic perspective on this because I'm a geologist and that's my training. In Antarctica, it's fun to think, you go back 150 million years ago, most of the continents are all collected in Pangaea, and they're slowly rifting apart. Antarctica's near the South Pole there. It's actually pretty close to where it is today, but it's a totally different climate regime there. 1, CO2 levels are 10 times higher, but 2, the way that heat is distributed through the ocean and atmosphere is really different when you pile all the continents together. And so you find dinosaur fossils in Antarctica, which is really fun, but that also tells you that it's warm enough for cold-blooded reptiles to live down there. And there's fossil trees, there's petrified, we found some petrified wood one day. So there were huge ecosystems in that time period because heat gets distributed in a really different way in that kind of world. And CO2 was 10 times higher, right? But slowly those continents are all rifting apart. And about 34 million years ago is when the Drake Passage, it's really South America is kind of the last thing. And I usually explain this as it's not that Antarctica and South America finally separate and there's like a cord that gets severed. It's really when the Drake Passage is open wide enough and deep enough to establish this Antarctic circumpolar current and get that going, which is the largest wind-driven current in the world. And that sets up ocean and air currents that are just circling Antarctica and make it really hard for heat and moisture to penetrate that and get through into the interior. It's kind of a giant fence that gets made. And so that's when Antarctica starts getting ice sheets and starts getting cold. Again, I like this long-term perspective here. So this is a classic figure to show time on this graph is on the y-axis. So it's 60, 70 million years on the bottom going up through time. We've got oxygen isotopes on the left, carbon isotopes on the right. These come from little foraminifera, shelly materials that live on the ocean floor and really reflect kind of deep ocean temperature and ice volume changes. So we can highlight the area 34 million years ago where there's this big drop in the global climate system when Antarctica finally separates from South America. We can see another drop at about 14 million years. In the Miocene, there's a drop, and then kind of a decline down into the Quaternary world that we're sort of in today, or that we're in the Anthropocene. But we start getting ice sheets in the northern hemisphere in the last 2.5 million years or so. So again, I like this kind of big picture kind of thing to set up with Antarctica. That it's been having ice for 34 million years. It gets really interesting, cold, and quite dry climate down there. And because it's so cold and dry, snow falls on there. It's a desert. It's only 17 centimeters of water equivalent of snowfall a year, but it just doesn't really melt. It just piles up thicker and thicker. So on the left, you can see, what's the bedrock underneath the ice. You can see the surface on the bottom left. So in the middle, that's really the ice thickness there. On average, it piles up to over 2 kilometers thick. It gets over 4 kilometers thick in a lot of places in Antarctica. And again, it's so cold and dry, very little melts. A little will actually go straight from solid to gas and sublimate. But it's so big and thick that as it flows out to the ocean, it's still so thick when it gets to the ocean, it doesn't just break off icebergs there. It often extends for hundreds of kilometers in giant floating ice shelves that eventually break off icebergs. And that's how Antarctica is losing most of its mass. So here's our illustration of these giant ice shelves that are out there. And that's really interesting because one of the key things in my Antarctica 101 thing is Antarctica ice volume is really driven by sea level. It relates a little bit to temperature and precipitation. Most glaciers in the mountains, though, you're really thinking about, well, how much does it snow and how much does it melt? And if those things are in balance, a glacier will stay the same size. If they're not in balance, it might get smaller, it might get bigger. But Antarctica is really controlled by where that grounding line is on that figure on the left, which is really impacted by sea level, a little bit of ocean temperature, though, but really mostly sea level. And of course, in the West Antarctica, a lot of Antarctica is grounded below sea level, and it's more of a series of islands than it is a giant continent. We talk about marine ice sheet instabilities because of that, because you can have some scenarios where if it starts to melt, it might rapidly decline. Whereas in East Antarctica, most of it's grounded above sea level, and it behaves a little differently because of that. So the other interesting thing about Antarctica is when you picture it, most people are picturing this, right? This is us flying across the Transantarctic Mountains on our way to one of our field sites. Everyone pictures giant snow and a few little mountain peaks sticking out, mostly covered in snow. 98% of it's covered in ice. I go to the weird 2% of the parts that are ice-free because when the ice sheet was bigger, it left behind the landforms in these valleys that we call dry valleys. And so you might see it's a nice big U-shaped valley. At one point, there was a glacier that came through here. All of that stuff that we're seeing, all that dirt is glacial till that was left behind by the glaciers that came through there. But this is not what most people think of when they think of Antarctica, right? And this is where we set up camps and collect our samples to really figure out how has the ice changed size over time. And the key thing here is that, again, it's really cold and really dry. So you get really amazing records and just interesting landforms out here, right? It doesn't have ants burrowing around. There's no bushes growing here. It's too cold and too dry for bigger life forms. It's not sterile. There are little microorganisms in the soil, but you get these kind of amazing landforms and interesting rocks, little puzzle rock things. They're actually just heating up and cooling, and they'll crack as a result of that. There's a lot of vent effects that are driven by the wind. It's kind of this amazing sculpture garden of eerie rocks. And it's that way because there's not rain coming on. There's not ants growing on. There's no bushes and trees, right? Or large animals knocking things over. And in these really cold, dry environments, you can actually preserve these landscapes for millions of years. It's almost like the landscapes are sort of freeze dried and they stick around for millions of years. So in Colorado, I said we get excited when we find deposits that are 120,000 years old. Here in Antarctica, we can, I got ahead of myself, but we find things that are often millions of years old. And then this is my other fun thought experiment, if you'll let me get a little distracted for just a couple minutes here. But it is really interesting to think, all right, big picture. How old's Earth? When did land plants evolve? And what did Earth look like before then, right? So we can put up a geologic time scale, and there are fun illustrations of this, but Earth's roughly 4.5 billion years old. And I don't know how much you might remember from biology or anything, but think about when did land plants evolve, right? So here's our geologic time scale again. We can think, all right, there's some first bacteria, 3.8, maybe 4 billion years old. We get a lot of oxygen in the atmosphere, about 2 billion years. But we don't really get complicated life till we get into the Cambrian era, right? So that starts about 540 million years ago, right? That's what we often call the Cambrian explosion as we start getting these things. The Paleozoic era as we get early life in there. And so I've hidden it in there, but first land plants are about 450 million years old. So one of the interesting things to think about here, if Earth is 4.5 billion years old, but we've only had land plants for 450 million years, we've only had grass for like 20 million years. I always kind of get blown away by that. So as we're out and we're hiking around, we're on these totally barren, vegetation-free surfaces. And I feel a little bit like a time traveler, right? Because this, even though it looks weird, this is actually kind of the normal state for Earth's surface, right? Most of Earth's history, there weren't plants on the surface. It's a geologist's paradise. It's just rocks, right? Now, I don't mean to say that it would have been cold and frozen, right? There would have been rivers. It would have been warmer in many places, but it would have looked a lot like this, which is why when I go down there with my students, I like to affectionately call them time traveling astronaut vampire penguins. And we feel a little bit like time travelers because you do almost feel like the helicopter dropped you off and you must have gone through some portal into a different era. These landscapes are where they test the Mars rover, and they are barren and rocky like the moon or Mars, and they're even getting all red and rusty like the surface of Mars, right? And vampire is the acronym the students actually came up for our latest project, the Vanderbilt Antarctic Moraine Provenance Immersive Research Experience, because every project needs a good acronym. So that's my group of time traveling astronaut vampire penguins last year. All right, so that was my little distraction. Back now to that point, which is we go to these valleys because they really have the world's best record of glacial history on land anywhere. They're so cold and dry. This is a map from Jane Steiger at the time, Jane Williamring now. She dated a bunch of moraines in Vernier Valley. There's a 4 million year old glacial moraine out there. And it's just sitting there, and you walk up and collect samples from it. It's incredible. And you just don't get that anywhere else on Earth. So part of the reason we go to Antarctica, if I sort of look at that, is that we get to then go look for deposits that are so old, they're really in this Pliocene epoch. And that's really interesting to geologists because that's the last time CO2 levels were around 400 parts per million. So we really want to know, what was the ice doing at that time frame? So the Pliocene is roughly 2.5 to about 5.3 million years ago, right? And so one of the amazing things that we can find out about going to Antarctica is, well, what was the Antarctic ice sheet doing in the Pliocene? And that might really help us make good predictions on where we're headed in the future. All right. So if summarizing that quickly, why do we go to Antarctica? Well, ice sheet's really driven by sea level changes. These are kind of the world's best record of glacial history that are left anywhere on land. And land's important because you can actually tell how much bigger it was. We get amazing records from ocean sediment cores, but you can't always tell exactly how much a specific glacier was bigger. But in Antarctica, you can because they're out left on land. And that's a really unique opportunity to study the Pliocene history of ice. All right, so a couple examples through here. I'll go through these fairly quickly because I know we want to hear from other people. If we look at modern thinning rates in the West Antarctic ice sheet, we're seeing things on the order of a meter per year, meter and a half, maybe just centimeters per year going on right now. There are some fairly large air bars in here, but we're feeling pretty good that we can tell that ice is thinning on the rates of centimeters to meters per year out here. So what do we see in the historical record? Antarctica, again, is a little different in the way we do this because we don't really get length changes as much as we often get more like thinning rates. We can go out to these high mountain peaks that stick up above the ice, and as the ice has thinned on them, it's leaving behind boulders, kind of like dirty bathtub rings. This is from someone on my PhD committee, John Stone. He went out to Marie Birdland. They collect a bunch of samples that were left behind as the ice is thinned, and they get rates on the order of centimeters up to maybe 1/4 of a meter per year of thinning since the last glacial maximum out here in Marie Birdland. We can go over closer to the Amundsen Sea and look for ice and same kind of style. This is closer sort of Waits Glacier area that we're seeing the most rapid thinning right now. And again, we see some rates that are just centimeters per year, but we also see some evidence of really rapid declines here, where within a couple hundred years, this may have lost 100 meters of elevation, right? So we're maybe up to 10 meters per year of ice lost, and really rapid loss in some places. So these are all from West Antarctica. Actually, a lot of my research is over in East Antarctica. So this is the Taylor Glacier, and this is Arena Valley, where it's a little hard to see on here. So I kind of drew them in here, but you might see some dirty bathtub rings on there. And oh, there they are. And so there's been dates, folks have dated some of these moraines. Eric Brown did this back in the 90s. That highest bathtub ring in there's about 1 million years old. It's just a couple hundred meters up from the ice today. So if we can calculate sort of a long-term range, again, this is the East Antarctic side that's not so susceptible to sea level changes. And we're getting rates of really, really low, right? So there are a lot of zeros in there. So I actually converted them to 25 centimeters per 1,000 years, right? Not per year, like we see in West Antarctica, but per 1,000. So 1,000 times slower, which is kind of amazing. We pop over to Beacon Valley. This is actually one that I dated in part of my dissertation work. And so this is Beacon Valley, beautiful, nice lateral moraine on the side there. We didn't find very good rocks to date, but so we actually dug a pit and took samples at different depths. Again, these cosmic rays penetrate a few meters in their surface, so you can do it. The key, we find lots of interesting things when we do pits, but the key thing is we get an age of about 800,000 years for this moraine on here. It's interesting. We couldn't find the million-year-old moraine, but we found one that's about 800,000 years in Beacon Valley. So again, rates pretty comparable, maybe 37 centimeters per 1,000 years for a long-term average. The last site I'll talk about is really fun, and this is one I could talk a ton about because this is a really fascinating valley. This is about halfway between where McMurdo Station is and South Pole. It's Ong Valley. The Argosy Glacier flows in through here. It's left behind this beautiful end moraine. This is one of the most stunning moraines I've ever seen in Antarctica, and it's just still right there, and it's kind of incredible. And so we collected a bunch of rocks all throughout this valley. I'll just highlight a couple of fun things that we did with this. In terms of trying to date that end moraine, we got a lot of boulder ages. There are limits to this dating technique with cosmogenic nuclides. Eventually, samples can become saturated in these isotopes. And so you just can't produce any more of them because the rock itself is physically eroding at really low rates. And so that's what's happened with this end moraine. It's reached the saturation value. So it doesn't necessarily give us an age. It gives us an erosion rate of about 40 centimeters every million years. So again, really, really slow erosion down there. But you can ask the question, you can flip that around a little bit and say, well, how long does it take to reach saturation? And at that rate, it takes about 7 million years to reach a saturation value. And so that may indicate that that moraine is a minimum 7 million years old and perhaps even older. And again, just like still there on the surface. It's incredible. The other really interesting thing is that in the middle of the valley, the glacial tills that are in there they're elevated a little bit. It's interesting. The oldest stuff is actually a little lower than the stuff that has to physically be a little younger. Otherwise, it would have gotten wiped out. And so we went back into this valley because when we were in there sampling and digging some of the pits, we actually found solid glacial ice under just a layer of about 60 centimeters of till. Again, what happens in Antarctica, it's so cold and dry that the ice comes in here, and when it retreats, it doesn't just melt away. Most of it here is sublimating. It's not breaking off icebergs. So it's sublimating away, and it means it's kind of just deflating like a balloon, but there's a little bit of dirt in it. So as you're sublimating, you're slowly thickening this layer of dirt on top of it. And now where it's at about 60 centimeters thick or so, it's really protecting that ice underneath it. So we went back. This is Marie Bergelin's dissertation project. Went back in there, dug up 2 10-meter cores into the ice. We can date how old the dirt is in the ice. We actually went through multiple ice bodies, which was interesting. We would hit dirt and then clean ice, and then we hit more dirt and then clean ice underneath that, so that at some point there had been what the surface we were on had been there, and then more ice had actually come over on top of that and gotten deposited. She was able to date these. We won't go through all the figures and the dating techniques because the concentrations of these things bounce back and forth because there were multiple periods of exposure, which was really challenging. But Marie was able to figure out that those 2 ice bodies in there, one's about 3 million years old, and the other one's 4.5 to 5 million years old, which is incredible because now we want to see what can we learn from air bubbles that are trapped in there, or pollen things that might be trapped in there, learn a little more about the Pliocene environment. This is more like a snapshot in time. It's not a continuous ice core where we're going to get a long record. We're going to get little details out of this, but these are really interesting. And actually, just looking at imagery and looking for these kind of odd shaped valleys that have an elevated sort of perched surface in the middle, we've identified maybe 20, 25 other valleys that might have buried ice areas in them, which is great because the oldest ice core we have right now only goes back about 800,000 years. Lots of folks are looking for older ice, but we can find stuff here that's 3 million, 4.5, 5 million years old, right near the surface. You don't have to drill a 4 kilometer ice core to get to it either. So that's quite an incredible archive that way. All right. So mostly I've talked about thinning rates and things. I'm going to try and leave you with a little bit of optimism here because this is really interesting work that just came out this year. Greg Balco was a grad student ahead of me at the University of Washington. We overlapped for a couple of years. I've spent 3 field seasons in Antarctica with them. So they went. What's really interesting about this project is it's kind of like some of the first ones I was describing, where you go to the mountain, you look for those dirty bathtub rings, and you date it. But then they went out with an ice core just a couple hundred meters off and drilled through the ice really quickly and collected rocks that are underneath the ice there. And the question then you can ask is, well, has the ice ever been smaller than it is today? And if it was, then those surfaces underneath it would get exposed and would build up these isotopes. And so one of the things we're interested in is, yeah, has the ice been smaller than it is today? So they went out there. This is pre-pandemic. They went out there and were able to get a bunch of samples collected and actually found that, yes, those surfaces under the ice have been exposed a little bit. The ice has to have been at least 35 meters thinner than it is today and expose these rocks a little bit. And that when you get really low concentrations, you don't get a great resolution. So we kind of say somewhere 3,000 to 5,000 years or so, the ice was 35 meters thinner and has actually grown and re-advanced since then back to where, well, it was even a little higher than it was today. And then it's declined a bit in the last couple of hundred years as well. But this is interesting because we are really questioning, are we going to reach some tipping points? Will the West Antarctic ice sheet fully collapse? If we pass those tipping points where we're stuck with some pretty irreversible change, this gives you a little bit of optimism that actually the ice sheet has been smaller than it was today. Yes, it did take a few thousand years to recover, so may not be able to do it eventually, but gives me a little hope that if we can really figure some things out, we may not totally ruin the West Antarctic ice sheet. And that gives me a bit of optimism. I like that a lot. And it's just worth saying too, like I've talked about how it's important to get the local information. This is a really amazing resource that actually Greg put together as well. He calls it the Informal Cosmogenic Nuclide Exposure Database. There's one for all sorts of different parts of the world. So I've just highlighted the Antarctica one here, but people are doing this all over and dating these landforms and to really piece together the history of ice all over the world. There's free data on here and you can collect things and make a lot of really interesting observations that way. And so if I just had to quickly summarize the stuff from Antarctica, what's interesting, at least in West Antarctica, since the last glacial maximum, we really see that things have been thinning on the rates of centimeters to meters per year. East Antarctica, though, is really much slower than that. We're seeing things that are centimeters per 1,000 years, right? And if we go back to the Pliocene, which we can date, we can say, all right, East Antarctica was a little bit thicker then. It's hard to interpret that very well, though, because in those scenarios, it probably decouples. It's probably retreat enough. It's decoupling from the ocean. And so it's not necessarily driven by just sea level at that point. And so it's hard to interpret that, at least for me as a geologist, and what that means for the paleoclimate record. But it's an interesting observation that in a lot of parts of East Antarctica, we do see higher moraines in the Pliocene than where the ice is today. And there's lots of other fun things we do in Antarctica that I'll skip through. But then just really to summarize this before I turn it over to my colleagues, just in those sort of paleo perspectives on making predictions, right? Doing this helps set these kind of baseline values that are interestingly in line with a lot of the observations we see, or that we can see that, all right, some of the observations are faster than what we've seen in the past, which is one of the reasons as geologists we get concerned about what's going on in the world today. And that I'll leave us with a little optimism to say that some of these glaciers have shown that they can re-advance if the climate is to stabilize. So it gives me a little hope. All right, thank you, and I'll turn it over to my colleagues.
Is not here, we have to do it ourselves. I talked too long, sorry. That's fine.
This is.
This is the introduction one.
Okay, so while this is getting settled, it looks good now. I'm going to thank Dan for the first presentation, which was a trip to the past. And in this session, now we are going to go travel through time. Actually, we have looked at the past, and now we are going to talk about future projections, which are indeed using past observations, not precisely these ones, but past observations to look and numerical models to look into the future. And so the next two presentations are going to be given by Regine Hock and later myself. And as promised, let's look first into the next century, and I'll go even further in time afterwards. So welcome, Regine.
Okay, thank you. So we switched timescales from millions of years to decades and maximum a century here. So I would talk about the global glacier meltdown and make the point that every increase in temperature matters. There are about 250,000 glaciers in the world, covering an area of 730,000 square kilometers, which corresponds to the area of Texas or the area of the UK and Spain together. And if all these glaciers melted, sea level would rise about 40 centimeters. Glaciers lose mass and they have lost mass and retreated worldwide in the last decades. Here are just a few examples. Here from Alaska, here from Iceland, just over the last 13 years. So you see massive changes within a very short time period in the recent past. Some glaciers have disappeared or are disappearing. Here an example from Bolivia, a glacier that has completely disappeared by now. Some regions have experienced extreme heat and extreme glacier melt, like in the European Alps in the last 2 years. Here in Switzerland, 10% of the total glacier volume has been lost in just 2 years, 2022 and 2023. On a global scale, there's an increase in mass loss rate. In the last years, we have an average melt rate here, an average mass loss rate of 50 to 60 centimeters water equivalent per year. So average over all glaciers worldwide outside the ice sheets, a decrease in the surface, a thinning of 50 to 60 centimeters per year. But there is, of course, large regional variations. So how will glaciers change in the future, in the next 100 years or until the end of the century? What you see here is annual mass changes projected by glacier models using a number of climate scenarios, climate projections. You see on one means 100% of mass in 2015, and then how much mass is remaining. So 0 means there's nothing remaining. And this for two emission scenarios here, the RCP 2.6, a low emission scenario, and RCP 8.5, a higher emission scenario. And what you see in all regions, there's a decrease in mass, how much mass is remaining over the century for both emission scenarios. And the global mass losses are about 20% for the low emission scenario, about 40% for the 8.5 or the higher emission scenario. And that corresponds to a cumulative sea level equivalent of about 8 to 17 millimeters by the end of the century. In areas where there's little ice at the moment, like in Scandinavia, the European Alps, or the low latitudes, for the higher emission scenario, what is projected is almost complete deglaciation. In areas that are sort of closer to the poles, like in Arctic Canada or around Greenland, their mass loss rates are less. So there still are, so the mass loss rates are about 10, 20, or 30%. Here is the same graph also for 19 regions here in the world, but now now it's expressed here as thinning rates, not in how much mass is remaining in percent, but the thinning rates. And here, like minus 2000 means that the glacier is, or the region here globally on average, it's a thinning rate of 2 meters per year. That's what that means. And it's quite interesting to see the difference here between the scenarios. For the high emission scenario, the thinning is steadily increasing in all regions in the world. But when you look at the low emission scenario, there's a constant or thinning rate, or actually less thinning with time. And that is with this scenario, which corresponds roughly to our 1.5 degrees, the glaciers are able to retreat to high elevations. Many will disappear, but those remaining can retreat to higher elevations where they can find a new equilibrium so that actually the thinning rates decrease. But for the high emission scenario, they steadily increase. Here are some scenarios. Now it's converted into global temperature increase by 2100 above pre-industrial. For 1.5 degrees, what you see here is for all the regions, all the pixels here that have glaciers, how much ice is remaining at the end of the century. And in blue means a lot of ice is remaining. In red means very little or almost nothing remaining. And the black circles show that where there's no ice left for a 1.5 degree scenario. And what you see is there's almost complete deglaciation for plus 1.5 degrees in many regions. Here you see plus 2 degrees. You see more and more red, plus 3 degrees, plus 4 degrees. So with plus 4 degrees, you only have a lot of ice remaining in the high Arctic, but many, many regions or sub-regions within these regions are deglaciated or very little ice left. And here you see for the mass loss in percent and the area loss in percent for global temperature change. And what is really interesting is this is almost a linear relationship. The higher the global temperature change, the higher the mass loss and the area loss. Here, for instance, for 2 degrees temperature increase, we have a 45% mass loss and an area loss of about 35%. So this really shows that every single degree matters. There's a linear relationship, not only in the global basis here, but also when you look at the different regions, same regions I showed before. In areas that have a lot of ice, the relationship varies in strength, but it's pretty linear. The higher the global temperature increases, the higher the mass loss. In these regions here, where there's relatively little ice, the relationship is more exponential because it simply doesn't matter anymore if it's plus 3 degrees or 4 degrees because the glaciers are gone. But what we really see is a very high sensitivity to global mean temperature increases here between 1.5 and 3 degrees. Makes a huge difference in these regions. Many glaciers will disappear. Even for the 1.5 scenario, what is projected here is that 50%, more than 100,000 glaciers will disappear by the end of the century. Of course, many of these are very, very small. The total volume that is projected for 1.5 degrees is lower. And yes, especially the small glaciers are disappearing. This is what we already see and witness at the moment. The glacier retreat impacts natural and human systems. And just to mention a few, sea level is affected, freshwater resources are affected, landslides are the stability of slopes, or it affects glacier outburst floods, water quality, landscape changes, and so on. And there's a session after this one focusing on glacier hazards. So every increase in temperature matters for global glacier mass loss. And so limiting the warming to plus 1.5 degrees is crucial to minimize these negative effects that the retreat has on sea level, stream flow, hazards, water quality, landscape changes, and so on. Thank you. So then we move to the next speaker, Fabien Monsieur from the University of Bristol in the UK.
Perfect. Thanks a lot. Thanks, Amy, also on the tech for having everything ready. I'm going to wait for the last bit. Can you hide the little? Yeah, perfect. Thank you. So we heard from Regine about the utmost important value of these glacier projections, which gives us which offer a window into the future, into what glaciers are going to do in the future. And what I would like now in this last few minutes now is to give you some insights on how these projections are done, the ones that Regine presented, but also the ones that some of you may have seen in the ICCI report. So here we are at the International Climate and Currency Initiative Pavilion, which on top of these activities, our COP is producing an annual report, which is a review of the state of knowledge about future changes in the cryosphere, not only mountain glaciers, but also ice sheets, permafrost, and much more. And so the work I'm going to present today is the work that has been realized to update some of the graphics in this report. And I'm here presenting, but actually the person who did the work is Lilian Schuster, collaborator at the University of Innsbruck and a PhD candidate there. So Regine showed us future glacier change until 2100. And here, this is more or less the same data, subset of it, showing glacier change. And as we've seen, so we are looking at a world at the end of 2100, when we look at mountain glaciers, so all the glaciers outside the ice sheets, with a global volume somewhere between 40% remaining in 2100 up to 80% of ice remaining, depending on the scenarios. The color give us the global temperature at the end of the century. And of course, this is the time scale which matter for certain adaptation projects, the next decades. What we find, however, is that first of all, we see that all these curves are not stopped, so they are not flattening. We see that glaciers are going to change even after 2100, and even if the climate stabilizes, because glaciers need so much time to adapt, to adjust to temperature changes, we already know that it's going to change into the future. And so what is not often done in glacier projections, for reasons I'm going to explain in a minute, is to actually look what happens beyond the end of the century. And this is what we have done here. So we are continuing this curve using climate scenarios which go further back in time up to 2300, which is the current end time in most projections offered by the IPCC or used in the IPCC. And we see a much broader range of outcomes here. And that's for several reasons. So the one is that glaciers continue to respond to past climate change after beyond 2100. And then it's because of so many of these scenarios, they continue past 2100, either with further emissions or with stabilization at a temperature level which is well beyond what a glacier can sustain. And so the range of outcomes is much larger. And what we see here is that our actions are going to matter at every time scales, 2050, 2100, and up to 2300. So I'm going to help you also to read these graphs a little bit, because they look a little bit complicated with all these colors and the scale on the right. So first of all, let's focus on the right-hand side here. What we are seeing here is a range of glaciers outcome, which shows glacier volume at the end of 2300 as a function of global temperature in 2100. And I want to emphasize this here because what we are talking about in these negotiations room now at COP is to limit the warming at 1.5 degree C. And this has to happen now during this century. And so what we're looking at here is at the temperature at the end of the century and various scenarios that humanity might take. And I'm going to argue very much to keep the blue scenario alive here. And so the scale shows us a range of outcomes, showing again that every tenth of temperature matters because every single little mark you see is showing a tenth of a degree, and we're talking about several percent of a global glacier volume each time that we warm the Earth a little bit more. But these graphs also show uncertainty bars because no one can certainly say that at 1.5 degree global glacier volume is going to be 70% for sure. We always give, when we do scientific assessment, a range of outcomes, and this is given by the box plot, so these bars next to our graph, and they show the uncertainty about the range of outcomes in a 1.5 degree world, a 3 degree world, and at 4 degree, you can see that the uncertainty basically vanishes because we have certainty that there is almost going to be no ice remaining on the globe at this very extreme global warming scenario. As a reminder, current policy are leading us toward a 3 degree world right now. Okay, so this is the same here, but in 2100. So I'm going to start then by the end and saying that our choice today will define the extent of mountain glaciation for the centuries to come. A world with more than 80% of global glacier volume is still possible today, but so is a world also without any glaciers if we continue to burn fossil fuels at the rate we are doing it right now. This is all in the report, and I encourage you to have a look at it if you haven't. It's available here in the room, but also as PDF online. Okay, so these graphs have been around since a long time in the report, and they look like this. And this was based on a study by Martin and colleagues in 2012, which here, for example, with the example of glaciers in the tropics, display a similar picture. So here, this is the tropics, not global. They display a similar picture that our decision matter, but I'm going to show you now the updated plot that we have realized this year. And you see that the picture is changing quite a bit with new research. Back in 2012, the state of the art was quite different than it is today. So despite of this work being extremely important, since then we have more climate projections for the future, and we have also more glacier models. So the graph on the right relies on 3 state-of-the-art glacier model, while the one on the left relied on 1. And for the graph on the right, we use all data available we have from remote sensing, from observations to actually calibrate the models. And for the same region, it shows a similar picture, is that very little ice is going to remain by the end of the century. But in the most in the scenarios at 1.5 degree, we see that there is a change as glacier stabilization, and as has been mentioned earlier, even at some regrowth depending on the climate variability in the specific location. Unfortunately, even if this is a message of hope, we can see also the time scales at which these glaciers might be growing, and it is very low. The reason we are seeing such large differences as well is that in between 2010, when these projections were made, and today, 10 years have passed, and the tropical glaciers are losing mass at a rate today, which is much faster than we can actually keep up with our models. Similar picture coming from the European Alps, where we see glacier loss no matter what. This is what we call committed glacier loss, as Regina mentioned, but also an outcome at stabilization and even regrowth in some scenarios. I want to stop here on high mountain Asia because this is the region where we are talking about the largest range in outcomes depending on the global temperature we reach by the end of the century, and therefore our actions today. And we've heard many times this week in the room about the challenges for adaptation and local communities in these mountain regions. And we can say for sure that keeping the world at 1.5 degree gives us an outcome with perhaps 80–70% of glacier volume remaining, and everything above goes very, very quickly into dangerous territory. Okay, so for the next few minutes, I'm going to stop talking about the outcome, the results, but talking about the science behind these graphs and how we actually generated them as a scientific community. It's never a one-person job. Lilian did the gathering of the data and the graphs, but actually it's always a community effort with different glacier models. So glacier model will have to encompass many of the processes happening on a glacier, such as this one. So you have snow cover, you have ice, and you have variability in between years. So here, this is extreme examples from the last 3 years in the Alps, where we see that the surface conditions of the glaciers are changing by a lot. Although we would like to be as precise as possible in simulating these processes, our models are going to have to focus on what matters and what matters most. And this is the interface between the climate and the ice surface. So simplifying things, I think taking reality and simplifying it for glacier models. The glacier models are going to have the task to simulate what we call the mass balance. And here I'm going to emphasize the climatic mass balance, which happens at the surface of the glacier mostly. So the interaction between ice and the atmosphere. What we call the mass balance is the addition of mass via accumulation, snowfall, avalanches, minus the loss of mass through melt and other processes. And the sum of all this is what we call the mass balance. And you've heard the term already in the previous presentations, and now I'm trying to put some arithmetic behind it. We have, at the end of the year, to make a balance, we make the budget of the glacier and we look how much mass was gained or lost. And this is a very useful diagnostic of a glacier health, because it gives us much information about if the mass balance is negative, then the glacier is going to lose mass. If the mass balance is positive, the glacier is going to gain mass. What it means for the dynamics, it means that if we have a gain of mass, so the blue area here is larger than the red area, it means that each year it's going to gain some ice and then it's going to advance as a result. And if it loses more mass than it gains mass, and the glacier is going to retreat as a result. This is not, I think, too complicated to understand, but in the context of our projection, it means that we have to have all these processes including in our models. And so when we build glacier models to make the projections we are talking about here, we take into account all these things. And so we are computing the flux of ice, and I'm not going to go through these equations, of course, with you. We are using climate data, satellite data, observations of in situ observations, people going on the glaciers and measuring the rate of change of these glaciers. And then, of course, we use supercomputer to implement these equations into a numerical model, and then we do analysis on these glaciers. And all these things are built into our glaciers models. And we do our best to implement all the processes I've talked just earlier. And so once we have a glacier model, we are feeding these glacier models with our climate projections for the future. And these graphs, I'm going to show many of them. They are a bit complicated, but I'm going to pitch you through them. These are exactly the climate projections we were talking about earlier, provided by CMIP, which is a member of which is providing data to the IPCC. So here on the top right here, what you are seeing are the scenario, which is represented here. This is emission scenario, which is supposed to limit the Earth towards 1.5 2 degrees. And here, these are the global temperature trajectories according to these scenarios and various models. What the spaghetti plots here shows is that the models do not agree, all of them, about giving us a certain emission pathway, how is our temperature going to look like? And this is an uncertainty we have to deal with because the Earth is complicated, basically. And so this also gives us information about what we talk about when we talk about carbon budget. The carbon budget is not a fixed number like 400 gigaton or whatever of CO2 that we have left to emit. It's really, it's uncertain, basically, because we don't know the Earth's response to our emissions. And so we are really advocating here for precautionary measures. That instead of talking about carbon budget, we should really focus on reducing our emissions as fast as possible, because even under low emissions, 2 degrees is not completely out of the possibilities. Similarly, 1.5 is still achievable, as we can see according to these curves. And then we do this for all these different scenarios, which all depict a different future of our emissions and of humanity, from the most optimistic to the most pessimistic scenarios. And the reason I'm talking about it now is that in our graphs, we have not talked about scenarios. We have talked about temperature targets. And we use these temperature targets because we believe they give a more understandable message to society and to our politicians as well. There is an uncertainty about the future temperature in the globe, and this is represented by all these potential outcomes different according to temperature, to emissions. We have an uncertainty, but glaciers, they don't respond to our emissions directly. They respond to our emissions indirectly via their influence on temperature. And so by looking at temperature in particular, we are providing a much more powerful message, is that the world needs to act to make sure that we stay in the 1.5 range. And if we manage to do that, then glaciers are going to respond accordingly because they respond to temperature. And this is why I want to go back now to this graph, which tells to decision makers and to us all that we have, first of all, to take a precautionary approach to our emissions to make sure that we stay below 1.5, given the uncertainties of the Earth response. And this is not sticking to a carbon budget. This is stopping our emissions right now, because we do not know if the Earth is not going to react actually more strongly than we already see it reacting right now. So the uncertainty on what we call the equilibrium sensitivity, the sensitivity, the equilibrium sensitivity is also needs to be included in our negotiations. And the simplest is simply to stop emitting fossil fuels now. I'm going to leave you there with my conclusions, is that we are using projections until 2300 because they show the scale, the range of outcomes on very long term. And glaciers might well disappear if we follow the current path of current policies. To make better decisions about the future, we need more lines, and I'm going to go back one slide now. We need more lines in this range between 1.5 and 2 degrees. We want to reduce these uncertainties. If we want to help practitioners, we really need to have more scenarios in the 1.5 range and much less in the higher emissions scenarios or the 4 degrees, 3 degrees world, because we don't want to see this world in the future. So we need to focus on 1.5 as the target, and what happens if, unfortunately, we are overshooting this limit due to Earth system response or because we are not quick enough in our emission reductions. That's it from my side. Thanks for listening, and I think this closes this session. Thanks, everyone. Good. Thanks, Amy. All good. Thanks.
I have a question for you, Fabian.
Okay.